Hello students, a very warm welcome. In today's lecture on chemical equilibrium, which is lecture 2, we'll be talking about law of chemical equilibrium and we'll be talking about equilibrium constants. So let's get started. First of all, we talked about this in the last class, some of it, right? What is the nature of chemical equilibrium? So chemical equilibrium was there, right? There was physical equilibrium, right? There was thermodynamic equilibrium. Physical equilibrium involved equilibrium between phases, right? Thermodynamic was when there was no heat energy or any other sort of energy being exchanged on a macro level, right? We're talking about chemical equilibrium, right? We started with it, we discussed a lot of points about it. Now we are moving forward with it. What is the nature of chemical equilibrium? Is it's dynamic in nature, right? Dynamic in nature, that means it can be established at different temperatures. So one thing you should know, for example, let's say there are reactants, right? There is, let's say, one reactant, let's say you've been given, right? And there are, I'll write this again, there are two products, right? And you want to know the stoichiometric coefficients of the reactants and the products, right? So let's say it's been given that the reactants, they go like this, right? And they reach equilibrium, right? And about the products, it's been given that it goes like this, right? First one goes like this, and the, let's say this is about B, right? This is A, and this the third product, this is C, somewhere over here, right? And it reaches an equilibrium, right? So guys, if you had to write the stoichiometric coefficients, what you could have done, if it was given that this was, let's say this is 3, right? This is 1, this is 2, right? Then you can very easily say that this difference, right? This would be the difference between these two, right? One would be the difference between A and C, and the difference between the stoichiometric coefficients of A and B would be 2, right? So if there is 3 is the stoichiometric coefficient of A, 2 would be the stoichiometric coefficient of C, and 1 would be the stoichiometric coefficient of D. So looking at the reaction, guys, right? So sometimes it might not be given that this is 1, 2, 3, but looking at the relative distance, right, you can figure out what could be the stoichiometric coefficient, right, of the reaction, right? This could come as a problem. We'll see some questions on it, right, later. So it's dynamic in nature, right? It's dynamic in nature. It's moving forward and backward at the same time, right? It's not stopping, right? It's not static, right? The equilibrium is not static. It's moving forward, it's moving backward. Both are happening at the same time, at the same rate. That's why there is equilibrium, right? So that relates to property number 5 also, that on the macroscopic level, the properties remain constant with respect to time, right? With respect to time. If you study from this moment to this moment, or from this moment to this moment, is the time interval is the same, you'll not, in fact, for all the time intervals, you'll not see any change in properties, right? On a macroscopic level, right? We also talked about this, that it's established in a closed system, right? If it was an open system, for example, if a gas was released as a product, what would happen is the gas would release the system entirely, right? So that wouldn't let the backward reaction happen, right? For the products forming the reactants back again, right? So I hope you understand that. Or if there is a liquid in the system, what will happen? It might evaporate if it's not a closed system, right? So there are various issues that you'll find if the vessel or the system or the dish that you're using is not closed, right? It's, of course, it's reversible, right? The chemical equilibrium, it's reversible, it's spontaneous, right? It's spontaneous. It does not require any energy from the outside to reach chemical equilibrium, and after that maintain chemical equilibrium. Once the chemical equilibrium is maintained, it will be maintained. You will not have to provide the energy from the outside. All right, I hope you understand. This is what spontaneous means, guys. This is what spontaneous means, right? Spontaneous in thermodynamical terms would transform into delta G, right? The Gibbs free energy being less than 0, right? Okay. It's not affected by the presence of a catalyst, right? So catalyst, what it will do is it will assist or aid the forward reaction by the same amount and the backward reaction by the same amount, right? So the effective result of the catalyst on the equilibrium wouldn't be any, right? I hope you've understood this, guys. I'll move on. What characterizes the equilibrium point for a reaction, guys? So what you should notice is, let's say you have a hypothetical reaction AA, right, plus BB is in equilibrium with CC and DD, right? Let's say it's not in equilibrium initially, the reaction is happening, right? The reaction is happening, right? It's still not in equilibrium, right? So what we define as the reaction coefficient, guys, reaction coefficient, it's defined by Q, right? The term used is Q, right? The capital little q, and it will be the concentration of C, the products, raised to the power their stoichiometric coefficients. It will be C raised to the power small c, D raised to the power small d, right? Over A raised to the power small a and B raised to the power small b. The reactants would come in the denominator, guys, right? So this is the reaction coefficient. So basically the reaction coefficient, guys, when this reaction coefficient becomes equal to the equilibrium constant, and now we'll talk about equilibrium constant also. So basically, guys, what happens is that the rate of forward reaction, you'll see when we talk about the next topic, right? The rate of forward reaction would be something like this, right? It will be K forward into the active mass of the reactants, which will be the concentration in fact, right? So A raised to the power A raised to the power stoichiometric coefficient, so A raised to the power B raised to the power B, right? And rate of backward reaction would be K backward into the active mass of the product. So it will be C raised to the power C and D raised to the power small d, right? I hope you've understood this, guys, right? So at equilibrium, the rate of forward reaction is equal to the rate of backward reaction. So this becomes, guys, this becomes equal to this, right? These two become equal. So basically what you'll have is this, right, is equal to K backward C raised to the power C into D raised to the power D, right? So the equilibrium coefficient, right, the equilibrium constant K equilibrium is basically K forward by K backward. We'll talk about this again, right? That will be equal to C raised to the power C over D raised into D raised to the power D over A raised to the power A into B raised to the power B, right? So basically at equilibrium, right, the reaction coefficient, right, the reaction coefficient Q, if it's given in the question, that becomes equal to the equilibrium constant K equilibrium, guys. That becomes equal to the equilibrium constant. And equilibrium constant, guys, this cannot be changed. This equilibrium constant cannot be changed. What that means, guys, is it cannot be changed by varying pressure or changing the volume, right, or changing the concentration, right? The only thing that can affect the equilibrium constant, this Q can vary, right? This Q can vary depending on the pressure, the volume, and other factors, right? But this K equilibrium does not vary. It varies. It's only dependent on temperature. Only dependent on temperature. That's it, right? It depends only on temperature. It's independent of everything else. The concentration at equilibrium is not independent of other things, right? Only K equilibrium is independent of other things apart from the temperature. So remember, K equilibrium, the equilibrium constant, right? We'll be talking about three equilibrium constant, Kp, Kc and Kx, guys. Those are independent of every other thing except temperature. So K equilibrium depends only on temperature. Please have that in mind. All right. Okay. All right. I'll move on. Please have a note of this. So at equilibrium point, what we've basically discussed is that the reaction coefficient Q becomes equal to the equilibrium constant, right? Okay. So law of mass action, which was proposed by Goldberg and Wage or Wage or whatever you want to say it, all right. So basically what it says is that the rate at which a substance reacts, right, that is directly proportional. This is not A, this is directly proportional to the active mass, right? So basically if we talk about the forward reaction, K forward, again I'm doing the same thing which we did in the last slide. K forward would be directly proportional to the active mass of A, right? Active mass of A, right? Active mass is basically concentration raised to the power the stoichiometric coefficient, guys. So it will be A raised to the power 2 in this case and B raised to the power 1, right? So if you remove this, so this is the rate, right? This is not Kf, this is the rate, right? Rate of forward reaction, right? Of forward reaction is this, right? So if you remove this proportionality sign, you will get a constant, right? That proportionality constant will be Kf, right? Kf, A raised to the power 2 into B raised to the power 1 will become the rate, right? And rate at which rate of backward reaction, guys, similarly would be equal to K backward into C, the stoichiometric coefficient of C is 1, so C raised to the power 1 and D raised to the power 3, right? Where this, what's indicated in this, right? What's indicated in these brackets, right? For example, this, right? D, right? These are the concentrations, right? So concentration raised to the power the stoichiometric coefficient, right? Concentration, I reminded you in the last class as well. I'll say that again, guys. So concentration is basically the number of moles divided by the volume, right? It's not the number of moles, it's the number of moles divided by the volume. I hope you've understood this, guys. All right, I'll move on. At equilibrium, what will happen is that the rate of forward reaction will become equal to the rate of backward reaction. So we'll get Kf, concentration of A raised to the power 2, concentration of B raised to the power 1 is equal to K backward, concentration of C raised to the power 1 and concentration of D raised to the power 3, right? Now Kf by Kb is the equilibrium constant, guys. K forward by K backward is defined as the equilibrium constant. I hope you've understood this, guys, and I'll move on. Please take a note of this. This is very important. Concentration is not the number of moles, it's the number of moles divided by the volume, right? What is K equilibrium? It's the ratio of K forward upon K backward that is reached upon equilibrium, right? K equilibrium is equal to the reaction coefficient Q at equilibrium, right? Only at equilibrium, right? The reaction coefficient Q is defined at various stages of the reaction, right? K equilibrium is the specific value of that Q, right, which becomes fixed after some time, right, when equilibrium is reached, right? I hope you understood this, guys. Next up, equilibrium can be achieved from either direction, right? Another thing about nature of equilibrium, right, it can be achieved from either direction. So if you're moving, if you have H2 plus I2, right, giving 2Hi, or if you have 2Hi yielding H2 plus I2, right, again both of them, right? So for example, if you are starting from over here, right, over here this is Hi, right? So the concentration, this is, let's say, the product. So the concentration of the product is increasing, right? And after which it becomes constant. The concentration of the reactant is decreasing, after which it becomes constant, right? And over here, if you notice, guys, we are talking about, from over here we are talking about time in this direction now. So if you notice, if you talk about the backward direction of, we talk about this, right, the second equation that we've written. So now the product becomes the reactant, so its concentration will fall down, right, and the reactant becomes the product, so its concentration will increase, right, and reach equilibrium. I hope you've understood this, guys, right? This is very, very simple, right? Moving on, what is law of chemical equilibrium? We've talked about this, guys, right? In a sense, we talked about this when we were talking about uh, K equilibrium, right? K equilibrium is the product of the concentration of product raised to their respective stoichiometric coefficient, right? At a given temperature, the product, this, right? So basically what this means is, this is a lot of story. What it means is that K equilibrium, guys, I'll use another colored pen. K equilibrium, which is K forward by K backward, is basically products, right? The product of concentration of products raised to their stoichiometric coefficient, right? So this is C raised to the power C, D raised to the power T, divided by the product of concentration of reactants raised to the power their stoichiometric coefficient. So this will be A raised to the power A and B raised to the power B, right? I hope you've understood this, guys, very well, right? We've repeated this quite a few times. So this is what the law of chemical equilibrium states. So law of mass action, law of chemical equilibrium, right? Law of chemical equilibrium is basically derived from the law of mass action itself, right? So remember, these are the concentrations raised to the power their stoichiometric coefficients, right? K equilibrium is when the rate of forward reaction is equal to the rate of, equilibrium is attained when rate of forward reaction is equal to the rate of backward reaction. I'm repeating again and again so that you can internalize it, right? K forward by K backward, the K equilibrium will come out to be, right, and it will be equal to this, right? We've derived this also. All right, I'll move on. So homogeneous and heterogeneous equilibrium, when all species are in the same phase, it's homogeneous equilibrium. So what that means, guys, is, for example, let's say the last reaction that we talked about, H2 and I2 combining to form 2HI, right? They are in gaseous state, all of them, right? So all species, all the reactants, all the products are in the same phase. So this is a homogeneous equilibrium will be attained over here, right? Or for example, if I say N2 plus 3H2 forming 2NH3, right? So this equilibrium attained is, again, all these three of them are in the gaseous state. So this is again a homogeneous equilibrium. A heterogeneous equilibrium, when more than one phase is present in the equilibrium reaction. So if I take an example, let's say CaCO3 when heated, right, it breaks down into CaO and CO2, right? CaCO3 is solid, CaO is solid, but CO2 is gaseous, right? So this is one example of heterogeneous equilibrium, right? Phases are different. I mean, all the phases are not the same. Even if one of the phases is different of one of the reactant or product, right, then we have a different, so then we have heterogeneous equilibrium. All right, I hope you've understood this, guys. I'll move on. All right, can we write the equilibrium constants for these reactions, guys? Yes, we can, right? Let's write it for the first one. The stoichiometric coefficients of all of them are 1, right? So K equilibrium, guys, would be, we take the reactants in the numerator. So PCl3, the concentration of PCl3 raised to the power 1 into concentration of Cl2 raised to the power 1, right, over the concentration of PCl5, which is the reactant, only reactant, raised to the power 1, right? I hope you've understood this, guys. Talking about the third one, let's do the third one first, then we'll do the second one. All right, so for this one, K equilibrium, for this third one, in fact, I'll write it again. For the third one, in fact, the K equilibrium would be NH3 raised to the power 2, right, N2 raised to the power 1, or just N2, the concentration of N2, and H2, the concentration of H2 raised to the power 3. right? Concentration we know is mole upon volume. So if we know the mole, we know more the volume, we can find the concentration as well, right? Of course, if you're talking about concentration and we say in moles by volume, this volume will be the total volume, right? I hope you understand. The number of moles will be specific to that reactant or to that specific product, but the volume will be the total volume. I hope you understand this. So this is K equilibrium for the second one, right? All of the three of them are in gaseous phase. Now, for the second one, guys, for the second one, what you should know, and I'll use another colored pen, what you should know for the second one is that calcium carbonate and calcium oxide, both of them are in solid phase, right? So, what do you think? Since they are in solid phase, don't you think that their concentration, that is mole upon volume, right, that would be the same, right? For example, if the reactant CO3 is getting consumed, at the same time the volume is becoming less, because it's a solid, right? For a solid, for a gas it could have changed, for a liquid it could have changed, in fact for a liquid also it wouldn't have changed, right? Specifically for a solid, if you talk about, the concentration won't change at any time, right? The concentration won't change at any time. So basically what that means is that when we are talking about ratios, right, or let's say when we are talking about the concentration of solids, we don't take that, consider that in K equilibrium, right? Or when we are defining rates, we don't consider the concentrations of solids, guys. All right. So basically what we will write in that case is, this is solid, this product is solid, this reactant is solid, only one of them, this CO2 is gas, right, not solid, that is. So we'll say that equilibrium constant will just be what? It will be CO2 and raised to the power 1, because the stoichiometric coefficient is 1. All of the reactant, all of the equations A, B, C are balanced, of course, right? So it will be just CO2 raised to the power 1. I hope you've understood this, guys, right? Very simple and very intuitive as well, right? And I'll move on now. All right. Now, this is very, very important, guys, right? So what we have over here is, let's say the equilibrium constant, right? K equilibrium for this equation is this, right? Now, if we reverse this equation, right? The equilibrium constant, let's say K equilibrium dash, right? For this one, for the second one, it would become 1 by K. So if you reverse 1 by K equilibrium, right? If it's K, then it becomes 1 by K, guys. It becomes 1 by K. I'll just delete it. It becomes 1 by K. Very, very important, guys. If you have a reaction and you reverse it, right? You write it in reverse, right? The new equilibrium constant will be 1 divided by the original equilibrium constant. So for this it was K. So for this it will become 1 by K. Now, if we are, first I'll talk about this point, right? If we are adding 2 or more equilibrium reactions, then K equilibrium for the resultant reaction becomes, for example, let's say if I have A plus B giving C plus D, and I have E plus, let's say, or let's say I have E plus C giving B plus F. Let's say we have this, right? And we add this, right? We've done this in class 10 as well, right? So basically what we'll do over here is, this C and this C will get cancelled, this B and this will get cancelled, we'll get A plus E giving D plus F, basically, right? So guys, what I mean is, if this has an equilibrium constant K1 and this has an equilibrium constant K2 and we add them, then what we'll get, guys, is that the equilibrium constant of the new formed equilibrium equation would be K1 into K2, multiplication, right? So I'll just write multiplication over here. If you add them, right? So basically, why do we have to add equations? Guys, we have to add equations because you see a reactant reacting with other reactants or perhaps breaking down on its own and giving another product, right? But actually, when you actually study it, right, what we'll see is that there are different transitions occurring. So this product gets converted into this product gets converted into this product, and finally you obtain something, right? So in such cases, guys, you'll have is you'll have equilibrium constants for different uh, reactions, right? And when you actually add them up, right, the final stoichiometry is maintained, right? The balancing, the conservation of atom, conservation of mass, everything is maintained. But the equilibrium constant for the final equation, guys, that is of relevance to us, which we study, of course, right? The in between equations we don't study, right? We would study when we are talking about organic chemistry. We are talking about transition phases and everything. We'll talk about that there. But over here, if you talk about this, then what you must understand is for the final reaction, right, that we have, the equilibrium constants of all the steps must be multiplied, right? So for example, over here it becomes k1 into k2. For example, if we have uh, Na plus Nb plus giving Nc, right? So if this has this the equilibrium constant for this, guys, don't you think it will become k raised to the power n, because we are adding this first reaction n times, right? So it will be k times k times k times k times k n times, right? So k raised to the power n, right? I hope you've understood this, guys. I'll move on. All right, if you try and solve this question, what do you think will be the answer, guys? Right? Again, a very simple question. Please pause and try and solve it. Give yourself 15, 20, 30 seconds perhaps. This is very, very easy. Right? Guys, I'll get to the solution. Guys, if you see, we are talking about K3, right? K3 in terms of K1 and K2, or perhaps K1, K2, K3, right? So basically, if you look at this, right? If you notice, if you add reaction 1 and reaction 2, you'll get the reaction 3, right? Because what will happen is that this CO and this CO will get cancelled, right? Also, what will get cancelled is this H2 and H2 will get added and give 2 H2O. This CH4 will come over here, right? This one CO2 will be over here. This H2 and 3 H2 will give 4 H2. So basically, on adding 1 and 2, you get the third reaction, right? So K3 is in fact K1 into K2, right? That's it, and that's our answer. K3 is K1 into K2, right? Option C. That's it. Done, right? Very simple question. All right. I'll move on. Let's discuss formation of NH3 Haber's process, right? And I'll explain equilibrium constant using that thing, right? So equilibrium constant, right? There are three types of equilibrium constant that we'll be talking about: Kc, Kp, and Kx. We'll be talking about just after this slide. But before that, what you need to know, guys, is that let's say we are talking about Haber's process, right? So Haber's process is N2 plus 3H2 giving 2NH3, right? All of them are in the gaseous phase, right? If you are writing, so for example, at T is equal to 0, let's say we have A moles of this, B moles of this, so there will be 0 moles of this, right? Let's say the time at which equilibrium is attained, right? Time at which the equilibrium is attained, at that instance, what we'll have is, let's say, X moles of N2 are consumed, right? So it will be A minus X. Now, it won't be B minus X, right? We've studied this in stoichiometry as well, right? It will be B minus 3X, right? And what will be formed over here? It will be 2X, right? So if you go and write the equilibrium constant, right? So K equilibrium, guys, would be equal to product raised to the power, concentration of product raised to the power their stoichiometric coefficients. We are talking about the concentration. So it will be 2x, right, divided by V raised to the power 2, right? Guys, do remember this, right? So if we are talking about concentration, initially it was A by B, V by V, right? Now it becomes this, right? So 2x by V whole square, right? The final volume at equilibrium is V, let's say, right? So the concentration, because 2x is the number of moles, B minus 3x is the number of moles of H2 at equilibrium, and A minus x is the number of moles of N2 at equilibrium. So 2x by V whole square over, this would be A minus x, I'll write it again, A minus x by V raised to the power 1, of course, and then it will be B minus 3x raised to the power by V raised to the power 2, right? So questions can come to find the equilibrium constants, where you will be given certain equations, you will be given perhaps the mole, the volume at equilibrium, and you'll have to calculate K equilibrium, guys, right? Or perhaps you might be given K equilibrium, the volume at equilibrium. You'll have to calculate the number of moles of each of the products and the reactants at equilibrium, right? That is 2x, B minus 3x, and A minus x, right? Whatever the value that is, right? I hope you've understood this, guys. This is a very important uh, methodology, right? It's a methodology, right? So you'll find it a lot in your solved examples, where whatever books you take up for this chemical equilibrium, you'll find it there, right? So just understand what is the method that we follow, what are the steps that we followed for getting K equilibrium in such cases, right? Don't forget. So this was number of moles, right? This was number of moles, this was number of moles, this was number of moles. We had to divide it by the volume to get the concentration, right? The volume at equilibrium. I hope you've understood this, guys, right? And now let's move on. Okay, so before that, let's talk about Kp, Kc, and Kx, guys, right? So the first thing that we'll talk about is Kc itself, right? So Kc, guys, is defining the equilibrium constant in terms of concentration, right? So what we've got from law of mass action, law of chemical equilibrium, that same thing, guys. So it's nothing but the concentration of reactants raised to the power. So if you have, let's say, AA plus BB at equilibrium with CC plus DD, right? So this will be simply C raised to the power C, capital D raised to the power D, capital A raised to the power small a, right? Capital B raised to the power small b, simply, right? Now, when we are talking about Kp, right, this is the equilibrium constant Kp, right, where P is for pressure, right? Now, when we are talking about Kp, guys, it's defined as the partial pressures. It's defined in terms of partial pressures. All right. So, for example, if we have again, let's say N2 plus 3H2 giving us 2NH3, all of them are in gaseous phase, homogeneous, right? No solids, right? So, it will be basically, and this partial pressure is basically defined for gases, and in gaseous state we've already studied that the partial pressure of gases can be expressed in terms of concentration, right? So in gaseous state what we've studied is that the partial pressure, guys, it's denoted by small p, is basically concentrations RT, right? So basically what we have by ideal gas equation is PV is equal to nRT. So if we are talking about P, it will be N by V into RT, and N by V we already know now is concentration, right? So basically CRT, right? So if you're talking about writing Kp in terms of this, so Kp basically will be, or it is defined as the partial pressure of NH3, so partial pressure of NH3 raised to the power its stoichiometric coefficients, which is 2, over, we'll definitely be talking in terms of stoichiometric coefficients, right? Because when you're talking about concentration, we were saying is stoichiometric coefficients. So stoichiometric coefficients are relevant over here as well, right? Right? Because if you're talking, if you have to relate concentration, the Kp and Kc, in fact, which we'll be doing, again we'll have to talk about the same thing, right? So PNH3 whole twice, right, raised to the power 2 over the partial pressure of N2 raised to the power 1, partial pressure of H2 raised to the power 3, right? This is what we'll have, right? This is how Kp will be defined, right? Now, if you notice, this partial pressure is basically CRT, right? So it will be the concentration of NH3, right? NH3 into R into T, and that is raised to the power 2. All of it is raised to the power 2, right? Over concentration of N2, right? Into RT, all of that raised to the power 1 just, right? So no need to write. Into, it will be concentration of H2 into RT raised to the power 3, right? So if you notice, guys, I'll use another colored pen now. So this would give us, what it would give is, it would give us NH3 whole twice N2, the concentrations, right, raised to the power the stoichiometric coefficients, and H2 raised to the power 3, right? Which you remember, this was the Kc part itself, right? This was the Kc part itself. And what you'll get is, you'll get RT, this is RT raised to the power 2 over, you'll get RT raised to the power 1. So finally what you'll get is, you get RT raised to the power minus 2, right? So basically this was Kc, right? And this is RT raised to the power minus 2, whole raised to the power minus 2. So basically, when we are expressing Kp in terms of Kc, right? So we'll define the relation between Kp and Kc now, right? The relation between Kp and Kc is that Kp is simply Kc times RT, right? K subscript C, this is, right, the equilibrium constant that we are defining in terms of concentration. RT raised to the power delta N, where delta N, guys, is the difference of the stoichiometric coefficients of the products and the reactants, right? So over here, if you remember, for N2 plus 3H2 forming 2NH3, it was coming out to be minus 2. So basically it was, right, N2 plus 3H2 forming 2NH3. So it was, this was 1, this was 3, so 1 plus 3, and because delta n is basically final minus initial, right? Final minus initial it is, so it will be 2 minus this, so it will be minus 2, right? And it makes sense also because the products come in the top, right? So over here delta n was minus 2, right? In this case delta n came out to be minus 2, hence we got it equal to Kc RT raised to the power minus 2, right? If we have a general reaction, let's say AA plus BB forming CC plus DD, and we have to find out delta N, it will simply be this small c plus small d minus small a plus small b, right? The product side minus the reactant side, the sum of stoichiometric coefficients, right? I hope you've understood this, guys, and please remember this relation, right? This relation is very, very relevant, and it's very, very simple also. You can very easily remember this, right? I hope you've understood this, guys. All right, I'll move on. All right, let's move on now, guys. The next thing that we'll talk about is the relation between Kp and Kx. So basically what they mean by X is the mole fraction. X is the mole fraction, guys, right? So guys, Kp, if you remember, guys, was what? It was partial pressure. If you're talking, let's say we take a reaction, right? N2 plus 3H2 forming 2NH3. Kp was partial pressure of NH3 raised to the power 2 over the partial pressure of N2 raised to the power 1 into partial pressure of H2 raised to the power 3. Right? So we have that over here. Now, guys, partial pressure of any gas, right? Partial pressure is defined as the partial pressure, small p, or I'll just write pp over here, right? The partial pressure, this is just partial pressure, so I'll just write partial pressure, right? And I'll say partial pressure over here. Partial pressure is mole fraction, right? Mole fraction, right? Let's say x1, x2, whatever the component we are, so in this case n2, whatever. So if you're talking about p of NH3, it will be the mole fraction of NH3 into the total pressure, the total pressure of the system, guys, right? This is the total pressure, right? So this is how the partial pressure is defined, and we know this, right? We've studied this in our previous chapters, right? So now, if you don't know this, please remember this, right? Okay. Now, this PNH3 whole twice can be now written as, if you notice, it can be written as XNH3, right, into what? Into the total pressure, right? That will be raised to the power 2 over Xn2 into total pressure, P total, right? And then there would be XH2 into P total raised to the power 3, right? Okay, and when you continue from over here, what you'll get is, you'll get XNH3 whole twice over Xn2 into XH2. This is whole twice, this is whole thrice, right? So the mole fractions, right? Into, if you notice, it will be P total, right? So P total, and what will it be raised to? It will be raised to, again, minus 2, which was delta n, right? This was again delta n, guys, right? Delta n, where delta n we talked about in the last slide as well, the same thing, guys, right? So basically, guys, what we have over here is that Kp, right, this we call Kx, right? So this is Kx. So Kx is defined in terms of mole fraction. So it will be, in this case, it will be XNH3 whole twice over Xn2 whole raised to the power 1 into XH2, the mole fraction of H2 raised to the power 3. Right? So Kp is basically, guys, it's Kx, right, into P total raised to the power delta n, right? And we've talked about delta n, right? I hope you've understood this, guys, right? This is important. So this topic of chemical equilibrium is very easy. I mean, it's relatively easy, not very easy. It is definitely relatively easy, right? So if you just pick up the concepts very quickly, what you'll realize is that the questions that will come across you from this topic are very scoring, right? So if you understand the topics, right, if you remember the formulas, in fact, by heart, and you have some sort of an understanding, you'll be able to crack the question, right? But have an understanding of how it actually came, right? And do remember that methodology I showed you, right? For example, in the Haber's process, right, I showed you for formation of NH3, right? If you remember, for this slide, I'll move on from over here. For this slide, formation of NH3, I showed you how it was coming out to be something like this, right? You remember? So it was at equilibrium, the number of moles and the total volume at equilibrium we were taking, and it was coming out to be, if I remember correctly, it would be 2x by v whole square and a minus x by v into, right, it was what, it was b minus 3x by v raised to the power 3, right? So the methodology that we adopted over here, that should be very clear, right? So this is the basic process that we do, right? And then you should remember P, Kp and Kc and Kx, how we calculate it basically, right? And you should remember the relation between Kp and Kc. You should remember the relation between Kp and Kx, right, guys? Great. I'll move on and we'll do this question now. All right, let's do this question. A moles of H2 and B moles of I2 are taken in a closed vessel of volume B at a particular temperature. Then find the expression for Kp and Kc if X moles of H2 dissociate at equilibrium. Right? X moles of H2 dissociate at equilibrium. So X moles of H2 are gone basically, right? So what we have is H2 plus I2 giving us 2Hi, right? This is what we have. So A moles, B moles, initially 0 moles. This is at 0. Time is equal to 0, right? So again, we are doing the same drill we did for formation of NH3. So at T equilibrium, right, the time when equilibrium is attained, this will be A minus X, this will be B minus X, and this will be 2x, right? So if you are writing kp, sorry, kc, it will be, what's the volume? The volume of the vessel is V, right? Taken in a closed vessel, the volume is V. So the volume, we are talking about gases, right? All of them are gases, homogeneous they are, right? So Kc would simply be defined as 2x by V whole twice over A minus x by V, right? Into B minus x by V, right? And what this simplifies into is, it simplifies into 4x square over A minus x into B minus x, because you can do the calculations, all the v's will get cancelled, right? So this is what we get for Kc. Now if we have to write Kp, we know that Kp is Kc times, right, RT, right, raised to the power delta n. And what will be delta n in this case, guys? It will be delta n would be 2 minus, this is 1 and this is 1, so 2 minus 1 plus 1, that will be 0. So in fact RT raised to the power 0 will become 1, right? So Kp will be equal to Kc. So whatever Kp is, the Kc value will be the same. So both of these will be the same expression for Kp and Kc, right? I hope you've understood this, guys, right? This methodology is very, very important. You will find this occurring, this methodology, at a lot of places, right? I'll move on. All right, we've talked about all this now, right? So in today's class we talked about law of chemical equilibrium, we talked about law of mass action, which from which mass law of chemical equilibrium was, we talked about the equilibrium constants, right? Kp, Kc, Kx, and the relation between them, and we did a few questions, guys. All right, so guys, please make it a point to revise the lecture, right? And if you have any questions, any doubts, please note it down, right? Also maintain notes. It's very, very important in any subject, especially in chemistry, to maintain notes, right? If you do all these things, you will be good. All right, so I'll see you the next time around.